Hello everyone, we are Group 1 and our topic is traffic signal optimization at the Gongguan intersection, and this is our group members. Gongguan intersection is a critical transportation hub connecting Taipei and New Taipei City, as well as Xinyi, Da'an, Yonghe, and Wenshan districts. During peak commuting and school hours, it handles approximately 15,000 to 18,000 vehicles per hour. Traffic signal control is therefore a crucial issue. Since the removal of the roundabout, traffic movements have become significantly more complex, as shown in the figure on the right, and there are many dashed lines which represent several spatial and less straightforward traffic movements. So our objective is to optimize the traffic signal plan and minimize the average waiting time per vehicle. For our data, we use traffic volume survey data from Taipei City open data, and mainly based on the 2024 dataset, which was the latest available data when we started the project. The dataset records traffic volumes during peak hours, including 7 a.m. to 9 a.m. and 5 p.m. to 6 p.m., including the number of motorcycles, cars, and buses, as well as the traffic flow from each entrance to different exits, as shown in the picture. Since the original data only provides the total number of vehicles in each 15 minutes interval, we used both uniform and Poisson distributions to simulate vehicle arrivals within each block. Due to the structure of the dataset, which records the total traffic volume for every 15 minutes interval, we adopted the same approach and treated each 15 minutes block as an individual optimization unit. So this not only aligns with the available data, but also helps us to keep the optimization model computationally tractable. As a result, the 3-hour observation period is divided into 12 blocks. By generating traffic arrivals under both the uniform and Poisson distributions, we obtain a total of 24 traffic scenarios for evaluation. So for our analysis, we group traffic movements into signal phases to better reflect real-world traffic operations and provide a clear structure for road users. And movements that can safely receive a green signal simultaneously were placed in the same phase. For example, go-through and right-turn movements in the same direction were grouped together, while left-turn movements were assigned to separate phases. To maintain a consistent and predictable traffic flow, we fix the sequence of these signal phases throughout the optimizational process, as illustrated in the slides.
Here are the decision variables used in our model. The subscript JK denotes the traffic movement from intersection J to intersection K. First, L represents the actual departure time of each individual vehicle. Next, G and E stand for the start time and end time of the green light in each specific cycle. Lastly, Z is the binary variable indicating whether a vehicle is assigned to pass through the intersection during the particular cycle. This slide represents the complete mathematical formulation for our model. Due to the time limitations, we will focus on objective functions and several key constraints or parameters, particularly those designed to capture important real-world traffic conditions. The objective function is straightforward. We aim to minimize the sum of the differences between departure time and arrival times across all vehicles, essentially minimizing total system delay. The first parameter we would like to introduce is the vehicle traversal time after it is allowed to move, which refers to the time required for the vehicle to clear the intersection once it leaves the queue. Different movements at an intersection, such as going straight, turning left, and turning right, often have different numbers of available lengths. To estimate the average traversal time for each movement, we assign a weight to each vehicle type, calculate the weight traffic volume, and divide it by the number of lengths available for that movement. The resulting value will then represent the average traversal time per vehicle for that specific movement. The constraint below describes the relationship between vehicle assignment and departure time. When Z equals to 1, it indicates that the vehicle is assigned to cycle N. In that case, its departure time must fall within a green interval allocated to the corresponding movement in cycle M. Next, the capacity-induced service limit constraint ensures that the number of vehicles served during the green phase remains realistic. The total traversal time must not exceed the effective green time available, which consists of the green duration plus L start. L start accounts for the initial delay before vehicles begin moving after the signal turning green. The constraint below enforces the temporal relationship between vehicle arrival and departure. It requires that a vehicle's departure time be greater than equal to its arrival time plus the traversal time. Since we introduced green line groups earlier, we need to ensure that all movement within the same group share the same signal timing. This constraint guarantees that all movements in a group receive the green signal simultaneously, consistent with the signal phase design. The constraints below impose an upper bound on a vehicle waiting time. They ensure that every vehicle is served within a reasonable time horizon and prevent excessive delays caused by the optimization process, so there won't exist a vehicle waiting too much time. When solving the model, we set a 30-minute time limit for Gurobi for each block. The figure below shows the result from 5 p.m. to 6 p.m. We can observe slight difference between the Poisson and uniform arrival settings, with the Poisson settings perform slightly better in this case. In addition, as the number of vehicles increases, the average waiting time also increases noticeably. You may also notice that the reported gaps are relatively large. We will discuss the possible reasons behind these large gaps later. During the morning peak, the model processed over 30,000 vehicles. The model keeps the average waiting time around 2 minutes even during the busiest 30 minutes window, the time from 7:45 a.m. to 8:50 a.m. This Gantt chart visualizes the generated signal timings. We choose one block to represent our result. The model dynamically adjusts the length for each green phase based on the real-time demand, while strictly adhering to the predefined phase sequence. Despite the promising result, the MILP model still has several limitations. The model contains thousands of binary variables, and certain parameter settings, such as the big M coefficients, can make the linear relaxation overly optimistic. As a result, the lower bound provided by the linear relaxation may be far from the true integer optimum, leading to the relatively large optimality gaps observed in our results. In addition, obtaining a proven optimal solution within a 30-minute time limit is extremely challenging. Once the time limit is reached, Gurobi returns the best feasible solution found so far. Consequently, the reported gaps may vary across different instances, resulting in the fluctuations observed in the experiments.
Next, let us introduce the heuristic algorithms we developed to overcome the computational bottlenecks of the exact MILP model. As previously discussed, when the number of vehicles and binary variables explodes, the Gurobi solver struggles to find high-quality feasible solutions within a reasonably time frame. To address this, we designed a 3-stage heuristic framework. First, we utilized the traditional Webster formula to calculate the baseline signal timing. Second, we apply simulated annealing for localized search to escape local optima. And finally, we employ a genetic algorithm to conduct a broader population-based optimization across the solution space. Phase 1 is the Webster formula, a classic and traditional analytical method in traffic engineering. It primarily calculates the theoretical optimal cycle length based on the flow ratio, specifically the ratio of critical lane volume to saturation flow, and allocates green time proportionally to each signal group. Although the Webster formula assumes steady state and uniform traffic, which cannot fully capture real-world dynamics, it is computationally fast, taking only milliseconds. We use the deterministic result as the initial seeds for our meta-heuristics, which significantly accelerates the convergence speed of our subsequent algorithms. In phase 2, we introduce simulated annealing, or SA. This is local search meta-heuristic. During the search, the algorithm introduces random, incremental adjustments to the current signal configuration, such as shifting green time between phases or adjusting the overall cycle length. If the neighbor solution yields a lower delay, it is accepted automatically. If it is worse, it is not rejected outright. Instead, it is accepted with a certain probability governed by the current system temperature. This mechanism allows the model to escape local optima early on, and as the temperature cools, the search stabilizes, yielding a significantly optimized local solution built upon the Webster baseline. The last method is genetic algorithm, or GA. Unlike simulated annealing, which improves one signal plan step by step, GA keeps many candidate signal plans at the same time. Each candidate represents a green time allocation for all phases in every cycle. We first generate several plans based on the Webster solution. Then, each plan is evaluated by the simulator, which calculates the total vehicle delay. A lower delay means a better signal plan. After evaluation, GA selects better plans as parents. Through crossover, it combines parts of two parent plans to create a new plan. Through mutation, it slightly changes green times or cycle lengths to explore new possibilities. Finally, elitism keeps the best plan in the generation. By repeating this process, GA gradually finds a signal plan with lower total delays. We compare 4 different approaches. The values shown in the table represent the average waiting time per vehicle. Green cells highlight the best performing method within each time block, while red cells indicate the worst performing method. As shown in the table, although the MILP model provides an exact mathematical formulation, it is subject to a 30-minute time limit for each block. Therefore, it doesn't necessarily find the best feasible solution before termination, but it still produces a reasonably good solution. In several blocks, both SA and GA achieve lower average waiting times than MILP solution. Webster method serves as our baseline. It is computationally efficient and can generate signal timings quickly. However, because it doesn't incorporate simulation-based optimization, its performance is generally less consistent across different traffic scenarios. In contrast, both SA and GA use the traffic simulator to evaluate candidate signal plans and iteratively search for better solutions. This heuristic method requires less computational efforts and also achieve better performance in most cases. This suggests that simulation-based heuristic can provide an effective and practical alternative for large-scale traffic signal optimization problems.
Now we want to share the variation of different cycle lengths upper bound, and we'll first clarify what a cycle is. A cycle refers to the time it takes for the traffic signal to complete one full round of all phases. So starting from G1, going through G3, G2, and so on, before finally returning to G1. And for our genetic algorithm, we establish 3 different search ranges for the cycle length. Setting A caps the maximum cycle length at 300 seconds. This is the exact same constraint used in Gurobi and SA, allowing for a fair comparison. It offers the most flexibility but might not perfectly align with practical intersection operations. Setting B restricts the cycle length to between 116 and 200 seconds. This is much closer to the actual 200-second cycle observed at the Gongguan intersection, making it the most conservative and readily deployable version. Setting C bounds the cycle length between 116 and 240 seconds. It provides more flexibility than setting B while still remaining within a practically acceptable range, essentially striking a balance between flexibility and practicality. This presents a performance comparison among our algorithms. Since Gurobi was given a strict 30-minute time limit per block, it still leaves a significant optimality gap. Even when we extended the time limit to an hour, the improvement was only marginal, meaning its results aren't necessarily the true optimal solutions. Webster serves as our baseline. It's incredibly fast, but it merely allocates screen time based on flow ratios without actively searching for the minimum delay. SA and GA, on the other hand, are simulation-based methods. They use a simulator to evaluate various signal planes and iteratively improve them. So as you can see from the chart, both SA and GA effectively reduce total delay and are far less time consuming than Gurobi. Then GA for model A, GA for setting B, and GA for setting C shown here use the identical GA framework. The performance variations simply reflect the impact of the different cycle lengths constraint we just discussed. So the key takeaway here is that our heuristics can find highly competitive signal timings in a fraction of the time. In addition to testing our models on real-world data from the Gongguan intersection, we wanted to evaluate whether these heuristic algorithms remain robust under different traffic conditions. Therefore, we designed 7 distinct traffic variation scenarios paired with 3 random seeds, generating a total of 21 test instances to verify the effectiveness and stability of SA and GA. These variations simulate extreme conditions, such as scenarios with a significantly higher volume of left-turning vehicles or a disproportionately large number of heavy vehicles. This figure presents the performance of our heuristics methods under several spatial traffic scenarios. As shown, the heuristics are still able to generate high-quality signal planes and maintain good performance even under these challenging conditions. So we come to the conclusion of our project. First, while the exact MIP model provides a rigorous benchmark, it is simply too slow for real-time use. Solving thousands of vehicle-level binaries variables is highly computationally expensive. Second, our heuristics find better solutions much faster. Both SA and GA utilize the same FIFO simulator and improve upon the Webster baseline. They can obtain competitive or even better signal planes within only a few minutes per block. Third, the GA with scarce cycle bounds represent our most practical results by keeping the cycle length inside realistic. Scarce compatible range model like GA for setting B and GA with setting C make the solutions much more deployable in real-world traffic settings. Lastly, we must acknowledge our limitations. Our current model does not account for the capacity of the connecting road segments. Furthermore, we have not factored in the delays caused by pedestrian for left and right turning vehicles. These are crucial areas for future optimization. Next, let's look at some real-world context. Based on news reports and public discussions, it is clear that many drivers experience excessively long waiting times at the Gongguan intersection during peak hours. For instance, people have mentioned taking more than 20 minutes just to make a turn. Others complain about red lights lasting over 100 seconds while the left turn signal lasted only for 5 seconds, forcing motorists to wait through as many as 3 red light cycles before being able to pass the intersection. Compared to these severe real-world observations, the average waiting time obtained in our experiments is successfully controlled to around 1 to 2 minutes. Being able to keep the wait time this short at such a massive control to around 1 to 2 minutes. Being able to keep the waiting time this short at such a massive and complex intersection proves that our model's results are practically acceptable. And this is our presentation. Thanks for listening.